Hello everyone. So previously we had discussed on the topic Johnson's algorithm, right? So today we'll be discussing on the topic Kruskal's algorithm, right? So let's get into the definition part. Let's see what the definition part say here, right? So Kruskal's algorithm is a greedy algorithm. So this is based on the greedy algorithm, right? So a Kruskal's algorithm is a greedy algorithm that is used to find the minimum spanning tree, also known as MST, of a weighted undirected graph, right? Again, let me repeat this. Just listen to this carefully. Kruskal's algorithm is a greedy algorithm that is used to find the minimum spanning tree MST of a weighted undirected graph. It works by sorting all the edges in the increasing order of the weight and this one and adding them one by one, ensuring no cycles are formed, right? So basically, it's a greedy algorithm used to find the MST of the weighted undirected graph. Just remember this undirected graph, not the directed graph, right? So it works by sorting, it sorts all the edges basically, right? In the order of the weight, in the increasing order of the weight, and adding them one by one. After sorting, it adds one by one. Uh, yeah, it adds the edges one by one basically, ensuring no cycles are formed. Simple one, right? Let's get into the definition part. Now let's break down how Kruskal's algorithm works step by step. First thing here would be we will sort all the edges of the graph based on the weights in the ascending order, right? So that's what the definition said as well. So we will be sorting all the edges of the graph based on their weights in the ascending order. Next, what we will do, we will initialize the disjoint set, right? So we are going with a DSU here, right? Just disjoint set basically. Union fine. We will initialize the disjoint set here just to keep track of the connected components. This is fine. This is fine, I believe. Next, let's move on with the third step here. Let's iterate through the sorted edges, right? After iterating through the sorted edges, if the edges connects two different components, then we have to include it in the minimum spanning tree. Yeah. If it forms a cycle, then we have to skip it. So that is the main thing. It shouldn't form a cycle. If it forms a cycle, then we have to skip this one, right? Again, within the iteration, if the edge connects two different components, then we have to include it in the minimum spanning tree. Or if it forms a cycle, then we have to skip it. So we will repeat the same process, this one, until we have v minus 1 edges in our this one minimum spanning tree. And v is nothing but the number of vertex or the vertices, right? So this is fine. The total weight of the included edges gives the minimum cost. So the total weight of the included edges, it will give us the minimum cost. So let's try to implement or articulate the same thing in the form of code, right? Uh, yeah, let's try to articulate the same thing in the form of this one algorithm or the code, right? So first, let's do one thing. Let's go with the first step. Let's define the class for the disjoint set, right? Union fine, I mean. So I'll just go with a class here, disjoint set, right? So within this class, let me do one thing. First, let's go with the initialization, right? So this will be def. Let me go with init here. Yeah, initialization constructor part basically, right? So along with the self, I'll just go with the n as well. So now let me go with self dot parent here, self dot parent. So this one I'll just go with I for I in range. So let me go with n, right? So this is fine. So each node is initially its own parent. We know this one, right? So next, let's go with a rank. Basically, it is used for the union by rank optimization. So I'll just go with here self dot rank. So this one will be 0, sorry, into n. This is fine. This is used for the union by the rank optimization, right? Don't get confused here, right? So let's move on with the further steps. Now let's go with a find function, right? So I'll just go with def find here. I need two parameters. One self will be present basically. I need one parameters, that is x, right? So this is fine. Now let's find the root of the set containing x with a path compression. So we'll be going with the path compression. So the name of the function itself is find. What we are finding here, we are finding the root of the set containing x with the help of the path compression, right? So I'll just go with simple if condition here, self dot parent. So self in the this one, what do we call? It's not entirely similar, but it's similar to the this keyword that you make use of within the JavaScript, right? In the Java, we can write it directly, but suppose if you're coding in JavaScript, we'll go with the this keyword, right? So it's not completely similar, but you can just make use of that's similar to the this keyword self within the Python, right? So I'll just go with X here. This one, if it is not equal to X, if it is not equal to X, then what we will do, I'll just go with self dot parent here, parent of X. Let me assign this one to the self find. So I'll just go with self dot parent of X. This is fine. Yeah. Now finally let's do one thing. Let's return here. Return self parent X. This is fine, man. Let me come out of this one entirely. Now let's go with a this one union function, right? So I'll just go with def union here. So this one self comma y, right? So this is fine, man. Let's go with a union two sets by the rank. Basically, let's go with root x and root y, man. So this will be easier. I'll just go with find of this one. What do we call? We have to pass x, right? Yeah, this is fine. Sorry. Let me copy the same thing here this line and let me make the necessary changes. I'll just go with y here, find of. So let me change this one to the y, right? So now let's write the simple if condition when root x, we have considered the variable root x when it is not equal to root y, right? So root x here not equal to root y. So let me change this one to the y, right? So this is let's write one. Oh, sorry. Let me write one more if condition here. So rank of root x is when it is less than the rank of root y. So this we are what we are doing here is, so we are going with a union two sets by rank, right? Rank optimization. Basically, I said this one first itself. It uses rank for the optimization, right? So I'll just go with here one more if condition. If rank of this one root x, this is fine, is less than this one. Rank of this one. What do we call root y? So I'll just go with root y. This is fine. Now I'll just go with parent root x. This one is fine. Root x. Let me assign this one to the root y. This is fine. I'll just go with the elif. Now let me go. Let me do one thing here. So this will be basically rank of root x. So we have already considered this one when it is less than, right? So let's go with when it is greater than basically. So let me do one thing. Let me copy the same thing here. So copy the same thing and make the necessary changes here. Just give me a second here. Yeah. So this one, I'll just go with rank of root x. If it is greater than rank of root y, then I'll be going with a self dot parent. So this one of root y is equivalent to the root x here. This is fine, I believe, right? So this is fine. Next, what shall we do after this? So there is one more condition. Else, what we will do? Else, I'll just go with this one. Let me copy the same thing here and give you self dot parent. This one. So this one root y is directly this is equivalent to the root x, right? So next, let's do one thing. Let me go with dot rank here. This is fine of root x. This one equals x plus 1. This is fine, man. Yeah. Now let's do one thing. I'll just go with a this one. If the union is successful, then we have to return true in that case. So I'll just go with the boolean value true. Else, if it is already connected, then we have to return false in that case, right? So I'll just go with return false. Yeah. Now we are done with this one. We are done with the union function or the method basically. Now let's move on with the next step, step two. So we have to define the Kruskal's algorithm function, right? So I'll just go with def Kruskal here. So let me go with a small case. I have went with small letters itself initially, the initial one basically for every function, other methods of the function. I'll just go with n along with the edges as the parameters. Right now, first, if you remember what was the first step within the algorithm, we have to sort the edges based on the weight, right? So I'll just go with edges dot sort here. So this one e equals, let me give lambda of x. This is fine. Let me go with x of 2. This is fine, man. Now let's do one thing. I'll just go with a ds. We are making use of the disjoint set, right? So the variable ds I'm going with. So I'll just go with here. Let me call the disjoint set of, let me pass n here. This is fine. Now, two more parameters we need here. Minimum spanning tree weight. Initially, we have to initialize that one to 0. Also, we need minimum spanning tree edges. We have to initialize that one to the empty array. Let's do that one. MST. I'll just go with a weight here. Let me initialize this one to 0. And also, MST. Let me go with the edges. Let me initialize this one to the empty array. Yeah. Now let's move on with the for loop here. So this one will be u v w in edges. So this is fine. Let's try to include the edge if it doesn't form a cycle, right? So this one will be if distance ds dot union. So this is fine. So let me pass here u comma. Yep. Within this if condition, I'll just go with the mst weight, this one, right? So this is equivalent to mst weight plus w. W is what we consider, right? The variable. Yep. Now let's go with the mst adjust here. This one, yeah. Let me append. What shall we append here? Let me go with u v adjust, right, and also w weight. So this is fine, I believe. Now we have to return what we need to return here. This one, weight as well as the edges. So we have went with a variable mst weight as well as the mst edges. Yep, we are done with the algorithm almost. Right. So now, yeah, we are done with the algorithm. Let's go with the example usage or the example graph, right? So let's go with a graph that is represented as the list of edges. See, we will be having u, v, weight. When I say list of edges, we'll be going with the edges, this one, u, v, as well as the weight, right? So I'll just go with here, edges equals, uh, yep, just give me a second here, 1 second. Yeah, let me do one thing. I'll just paste it over here, right? So this is fine. Yeah, let me put that just here. 1 second. So this is fine. Also, this is also, yeah. Now let's do one thing. So the number of vertices we have here is 4. Basically, the number of vertices we have here is 4. Let's consider here n equals 4. Also, this is nothing but the number of vertices. Let's move on with the next step. Nothing but let's run the Kruskal's algorithm. So I'll just go with here MST. So why this is not showing here? Did I do anything wrong? Everything is fine. Let me format the document once. So this one I'll just give here. Let me type instead. MST weight, comma MST edges here. So this one let me call Kruskal. So this is also not showing. Hey, what happened? What's wrong here? One second, just give me a second, man. So this is the example usage. Let me do one thing. Let me copy paste the same thing here. So see here, the same thing. So here we are just outputting the results. We are making use of the print just for the interactive purpose. So I have given here edges in the minimum spanning tree. So this one, just the for loop, right? So finally, we are just going with the total weight of the MST, nothing but we are this one displaying the minimum spanning tree weight basically, right? So this is it for the algo basically. Algorithm stopped here itself. I have explained till here. So this is the example usage. So I can just go through this one, right? So let me do one thing. Let's run the code. We have the idea on the algorithm. We went step by step, right? So now what is the output that we need to get here based on the this one edges or the graph that we considered here? So this one edges in the minimum spanning tree is this one. So basically it would be 2 followed by 3 actually. So this is equal to 4. So this one edges I'm considering. And 0 to 3. So this one you can just consider here. This is equivalent to the value 5, right? So this one I'll just give double equals here. And 0 to 1. So this one we should be having 10, right? So total weight of the MST is the last one, this one basically. It's sorry, it is the sum of this one, right? 10 plus 5 plus 4 basically. So this will be 10 plus 5 plus 4, right? So this one has to be 19. The output has to be 19, right? So edges in the minimum spanning tree 2 to 3, 0 to 3, 0 to 1. You can ask if you still didn't understand. Let me tell you how it is 2 to 3, 0 to 3, 0 to 1. See, 2 to 3 equals 4, whatever I have written. So the smallest edge is 2 to 3 basically with the weight 4. It is added 4, right? So it is added first. So this one we are considering this one, right? 2 to 3, this one. The smallest edge is 2 to 3 with a weight 4. It is added first. So we have added this one first, right? So I hope this is clear now. Next smallest edge is 0 to 3. This one, the second one. So basically, this is the second one. This is the first one, right? This is the first smallest edge, and this is the second smallest edge. So we have added the second smallest edge from 0 to 3, which is equivalent to the 5. So no cycle is found here. So we have successfully added this one. This is fine. Now the third smallest one is this one, 0, 1, 10. Right. So this one, the third smallest one is this one. Here also no cycle is found. So we will be we have added this one successfully, the edge 0 to 1 with the value 10, right? So nothing but the weight, you consider this one value as the weight, right? So here this is fine. The next smallest edge is 0 to 1. Still no cycle is found here. We will add this one as well. Now what we will do, total weight is equivalent to the sum of all the this one, what edges that we have added, right? Uh, Smallest edge 1, 2, 3. So this one basically that we have found. So this will be 10 plus 5 plus 15 or 4 plus 5 plus 10 it is. So we can just consider in any way, right? So I have not considered this one in the order, but still this is fine, right? So 10 plus 5 plus 4 we got here as 19. So the total weight is 19. So the output that we need to get here is 19 basically. Now I hope this is clear, man. Now I hope this makes sense, right? Yeah. So now let's do one thing. Let's quickly run the code. So I'll just come here. Let me give Control J. Let me run this one, man. I'll just give here Python followed by the file name. So let me copy entire file here. This is fine. Give enter. So we have some error here. What happened? Name kruskal is not defined. Mhm. Give me a second here. We have defined the kruskal, right? So what's wrong here? One second, just give me a second here. Uh, mm, have we written anything wrong here? This is fine, man. One second.